Hello everybody. In this course, we introduced you to a Kenlayer software that is used for determining stresses and strain at different locations of the pavement. In the previous exercise that we solved using a Kenlayer software, we used elastic modulus to determine stresses and strain at different locations of the pavement. Now, you know that we use a resilient modulus in place of elastic modulus in the pavement analysis. In such case, resilient modulus of a granular material or soil material is stress dependent. Now, the question is how to account this stress dependent material property in the analysis of pavement. So, we will solve this exercise using a Kenlayer software. You have been already introduced to a stress dependent resilient modulus value of a granular layer and soil layer by Professor Nivita. Now we will have a glance into these equations and we will focus on the material properties so that we can use these material properties in our analysis. So you know that the granular layer and the soil layer exhibit a stress dependent modulus, and modulus of a granular layer can be given by this expression where E is a resilient modulus here, which is equal to K1 theta over K2. So when you measure a resilient modulus of a granular layer for different stress invariant, you can see that the resilient modulus exhibits a straight line function when you plot it in a logarithmic scale. So the constant, the intercept here is called as a K1 value, and the slope of this line constant is K2 here. So this value of K1 and K2 depends on the type of a granular layer. So you can see that for different types of granular layer, the K1 value varies from 1620 psi to 7210 psi, and K2 value is somewhere nearing 0.5. So if you can determine this value of K1 and K2 by conducting a resilient modulus test in the laboratory. If you do not have such kind of a facility, you can infer to the value of K1, K2 value from this reference table. You can also see that the resilient modulus of a granular material increases when the stress invariant increases. This is the resilient modulus of a granular material. But if you see a resilient modulus of a fine grained material or a soil value, it decreases with the increase in deviatoric stress. And you can also see that there is a two-stage slope curve for a resilient modulus of a soil layer. So to define this resilient modulus of a soil layer as a function of deviatoric stress, you need four constants K1, K2, K3 and K4. The K1 here is the resilient modulus value at a point of slope change. K2 is the deviatoric stress value at a point of slope change. K3 and K4 are slopes, two different slopes. So you can mathematically represent this line using these two equations given here. So again, you can determine the resilient modulus value in a laboratory for different deviatoric stress and measure this constant K1, K2, K3 and K4 for the analysis purpose. If you do not have a laboratory values here, determined value here, you can infer to this chart for different K1, K2, K3 and K4 values. So you can see that the K1, K2, K3, K4 value varies depending on the type of clay soil. So you have for four different clay soil, very soft, medium and stiff clay. You have material parameters listed here. You can also see that there is a minimum value of K1 and minimum value for resilient modulus is defined for different materials here. So we will see how to use these parameters in the analysis. So Kenlayer uses this pressure dependent material property in the analysis, and it is called as a nonlinear analysis. So what exactly the nonlinear analysis in the Kenlayer means is we account into the stress dependent material property in determination of stresses and strain. So this nonlinear analysis is carried out only for a granular layer and a subgrade layer. So we get, when we determine stresses and strain at different locations, we get normal stresses. We get three normal stresses, and these three normal stresses is going to depend on depth. So if the depth, normal stresses varies at different depth, the modulus at the depth is going to vary. So in such case, the stresses and modulus are interdependent parameters. So what Kenlayer does is, it assumes the initial seed modulus value and determine the stresses and back calculate the modulus value using the equations that we have seen previously, And so this process is iterated many times, so the solution converges. So for this purpose, Kenlayer uses three different approaches. So in the first approach, what it does is the entire base layer is divided into small sub-layers. So after dividing into a small sub-layers here, the center point of each layers are defined as a stress point. Now, with the knowing the seed modulus value, the stress value, normal stress values, that is sigma 1, sigma 2, sigma 3, or you can call it a sigma x, y and z, that is stress at different normal stress at x, y and z direction. So, you get the normal stress value. From this, you can compute the modulus value here, and this process you can iterate till the solution converges. So, if in some cases, if for determining the stress invariant, you can also include a dead weight of the material above, where here gamma is the unit weight of the material, Z is a depth at which we are interested in finding the stress, and K naught is a passive earth pressure constant. So, you can see that the stress invariant depends on the normal stress. See, sometimes these normal stress can also be a negative value. So, this negative normal stress occurs when you go deep below away from the loading conditions. In such cases, if you get a negative normal stresses, that negative normal stress value is adjusted to 0 value for determining the stress invariant in these conditions. So, this is the first method. In the second approach, it is not divided into sub-layer. The entire base layer is considered as a single layer. So, now when you consider entire base layer as a single layer, the next question is which point we are going to determine the stress and then the modulus value. So, the second method uses a stress point as a 1/4 of the height of the base layer. So, if H2 is the height of the base layer, 1/4 of the height of the base layer is considered as a stress point for determining the modulus value. So, you assume a seed modulus value, determine stress at this locations and then compute back the modulus value and iterate this process. So, while doing this process here, since this point is very nearing to the loading conditions, so there may not be any chance for the negative normal stresses. So, you don't need any kind of adjustment here. So, you can consider a normal stress even if it is a negative value, it may be a very small value. So, you can consider a negative normal stress as such. Since you have a negative normal stress compensating on the vertical normal stress, so we define a minimum modulus here. So, the minimum modulus here is defined as the K1 parameter that we have seen for a granular layer. So, the minimum value is considered as a K1 value, minimum modulus value. So, the modulus will never go less than K1. So, this is a method 2 approach. In a method 3 approach, the stress point is considered as a midpoint of the granular layer. In such conditions, as the midpoint is away from the loading conditions, there can be a chance for a negative normal stresses. So, you need to adjust the principal stress values or sigma normal stress value so as to avoid this negative value in the stress invariant. So, this adjustment is carried out using a Morse-Coulomb theory. So, you have a relation here sigma h, which is nothing but the horizontal stress, equal to sigma v vertical stress tan square 45 minus 5 by 2. So, here phi is defined as a cohesion of the soil or as cohesion of a granular material. So, you need to define a phi value. When the phi value is 0, you will get sigma h to be equal to sigma v. So, sigma h is adjusted and then modulus is recalculated. So, this is a third approach which the Kenlayer uses. Now, we will solve this numerical using a Kenlayer software. So, you have a 3-layered structure as shown in the figure below, and it is subjected to a single wheel load, and the single wheel load has a pressure intensity of 75 psi and the diameter of the load application is 9 inch. So, we will as such use inches and psi for the solution here. So, now we need to determine what is the maximum tensile strain at the bottom of a layer 1 HMA layer and maximum compressive strain at the top of a layer 3, that is a subgrade layer. So, we will use a 2 approach here, which is method 1. So, method 1 is dividing a base course into multiple layers and determine stresses and strain at critical locations. And method 2 is we consider a layer, second layer as an entire one layer and determine stresses and strain, but for the modulus determination is considered at upper quarter point of the layer 2. And so when we go for this nonlinear analysis, so when you open a new file in a Kenlayer software, so you will have a first general menu options. When you click on this general menu options, this is what the informations we have to give. So type of material here is a nonlinear. Unlike previous problem, we used a linear analysis, and keep in mind that this is called as a nonlinear analysis because we use a modulus as a stress dependent modulus. And so nonlinear analysis, so we select 2 here, and we don't perform any damage analysis here, so we'll keep this as 0. Number of periods per year is 1, number of load group is also 1. We are not doing a multi-group and a multi-load analysis here, so we'll keep it as 1. And number of layer here, see it's a 3-layered structure, but we divide a base layer into small layer. Let us divide the base layer with each layer of 2-inch thickness. So the total thickness of the layer is 4 inch. We will divide into 2 layers, each of 2-inch thickness. So you'll have 2 base layer, 1 HMA layer and 1 subgrade layer. So total layer will be a 4 layer here. So number of Z coordinate for an analysis, one is for fatigue strain corresponding to the fatigue damage, another is strain corresponding to the rutting on the subgrade layer. So you have 2 Z coordinate for the analysis. So these iterations, numerical integration, type of response, interface bounded, and number of layers at the bottom, tension and top compression, this you are already aware of it. So we will move to the next input, Z coordinate. So this Z coordinate, when you give, since we are given 2 Z coordinate, one is at the top of a subgrade layer. So top of a subgrade layer, which is nothing but 12 inches. So I have just given 12.0001. So that the point is exactly lies on the subgrade layer, not at the interface. And this other one is Z is 8 inches, which is nothing at the bottom of an asphalt layer. So you give this as an input, 8 inches and 8 plus 4, so 12 inches as an input parameter here. Now the next input is an Z layer input, which is a thickness of different layer. So 8 inch first, and the second and third layer are base layer. So we divided into 2 inch, 2 inch each. So the 4 inch of the base layer is divided into 2 layer. And the third layer is of an infinite thickness. So you have an infinite thickness here already defined. Poisson's ratio of the first layer is 0.45. Second layer and third layer itself is a base layer and its Poisson's ratio is 0.3. And the fourth layer is a soil layer that has a Poisson's ratio of 0.4. So gamma here is defined, which is nothing but the density, which is pounds per cubic feet values. So the gamma value which is given in the numericals are given as an input here for determining the self weight of the material. And then this self weight of the material will be used in the computation of a stress invariant. So now next input is a moduli value. So now when you see the moduli value, we have used only one period here. When you click on this, you will get the modulus value. Now if you see the modulus value, we used a modulus E1 to be the modulus given as a modulus of an asphalt layer. See this modulus of an asphalt layer, this asphalt layer is going to be an elastic layer with the same elastic modulus, and it is only one value. Now if you consider a base course, now this is a resilient modulus value and it is a stress dependent resilient modulus. So and it is defined by this equation here. So this equation says K1 value is equal to 10,000 psi and K2 value is equal to 0.5. Now we need a seed modulus value. You can assume any seed modulus value for base layer. So you have 2 base layers of 2 inch thickness. So I have just given 2 different modulus value, seed modulus value. So likewise you can take some other seed modulus value for a soil layer also. So soil is also considered as a pressure stress dependent modulus value. So here it is given that we use a soft clay. I just assume some seed value modulus here to be 5000 psi for determination of stresses and strain. So once you give the modulus value, the next input is a load parameter. So now if we have a single wheel load. So single wheel, single axial is defined by load group 0. Contact pressure is 75 psi and contact radius is 9 by 2, which is 4.5 inches. Since it is a single axial, single wheel, there is YW to be 0, no wheel, there is only one wheel. So center to center distance between two wheel is 0, center to center distance between two axial is 0. So we are interested in determining stresses and strain exactly at the center of loading. So you just click on this NR and give this input to be RC to be 0, which defines the center at the point. So we define a stress value. We need to find out the critical stress value at the interface of two layers. Okay, but to compute this stress value, you need a modulus value. This modulus are computed using a first method, that is by dividing this base course into two layers, each of 2-inch thickness. 2-inch thickness, and the mid of each layer is defined as a stress point, and the modulus value are determined from the mid of this layer. So now the next input is a nonlinear input, which is something very new to you. So in the nonlinear input, if you click, you will get these options: general, relaxation, non-seasonal input, seasonal input, and most Coulomb theory input. So we use, when you click on this general input, this is the information you have to given for the analysis. One is number of nonlinear layers. So how many number of nonlinear layers we have? We have two base course and one subgrade layer. So you have number of layers to be 3. Maximum number of iterations, as this modulus is computed based on the iterations. So maximum number is restricted to 5, 15, and tolerance for numerical analysis is 0.01. So now these radial coordinates, x coordinates and y coordinate value, and slope of load distribution is defined in this figure. So now assume like this is the radius of the load. As of here, now this is 4.5 inch. So now see, the point at the top surface will get transferred to the at any depth z in a depending on the slope of load distributions. So if you define a slope of load distributions, you can find out what exactly is the radius x and y coordinate at any depth using this equations r, x and y. So you need the parameter to be defined here. What is ZCN OL, or what is the slope value, what is the radius value, what is the x and y value. X and y is applicable in case if you have a 2 wheel loads or at least 2 wheel loads. So as of this, for this input, we assume that the slope here is 0, and we will give all these input to be 0. Since slope is 0, exactly the capital R will match with a small r value here. We don't have x and y here because it is only a single axial, single wheel. So once the general input is done, the next one is a relaxation input. This relaxation input is a factor used for the convergence of the modulus value, and by the default value is given as 0.5. You can use the same default value. The next input from the modulus is a non-seasonal input, in which where we define the constants here. In the non-seasonal input, so you have parameters here. We define the layer number. So second layer, third layer and fourth layer are for the nonlinear layers. So for second layer, now the value at which we need to find out stress. So it is exactly value at which we need to find out stress is exactly this point, which is 8 plus 1 inch, which is 9 inch. So third layer is 8 plus 2 plus 1, which is 11 inches. So the value where the modulus to be determined is, for the first layer it is 9 inch, for the second layer it is 11 inch, and for the that is subgrade layer it is 1 inch below the interface. So it is 4 plus 8 plus 1, so it is 13 inch. So now whether to define whether it is a fine grain soil or a granular layer, we use this N clay. So if you give N clay to be 0, it represents the granular material. If you give N clay to be 1, it represents the clay soil or a fine grain soil. So now when you click on this n clay value, you will get this parameters, that is non-seasonal input parameter, that is a value of K2, which is nothing but the slope of a resilient modulus value, and we have seen that this value was close to 0.5. So by default, this value will be taken as 0.5. If you have any other number other than this 0.5 based on your experimental results, you can use those number here, and K0 is a earth pressure constant, and in the numerical values it is given as 0.6, so we will use the same number over here, 0.6. Now if for a N clay, which is if it is a fine grain soil, so you will have 4 constants, that is excluding K1 you will have K2, K3, K4. So all these 4 constants values, these are the default values which is used here, and the earth pressure constant for the clay soil is taken as 0.8. So these are the non-seasonal input which is going to be same for any number of period. So there are some input, that is a value of K1 is dependent on the period. So we have defined here only one period. And so we will give a seasonal input here for only one period, and we have 3 layers. So you can give an input for all 3 layers. So when you click this layer 1 for that is layer 2, second layer, so you have to give the value of K1. So the K1 value as per a numerical, it is 10,000 psi, and you also define a minimum value of a K1. So minimum value of a pi represents a minimum value of K1, it is taken as 0 here. So for this is for the granular layer. Now for a fine grain soil or a clay soil, now that is a layer floor subgrade soil, you give what type of clay it is. So for very soft, from very soft, medium and stiff clay, so the number here defines what type of clay. So you go from 1, 2, 3 and 4 here. So you give it's a soft clay. So when you click on the soft clay, these are the minimum parameters used. See, you already saw that you have a minimum value defined for a soft clay, maximum value defined for the soft clay, and K1 value used for the soft clay. We give that as an input parameters. You can also get these parameters value from the experimental results. So once you give this parameter, your nonlinear input is done. So after giving this, just save and exit out of this main menu options, and you run this program using a Kenlayer. When you compile it, so you will get the screen something like this once the compilation is complete. So this says that this is the number of iterations it has taken to compute the modulus value at subgrade layer and the base layer. So once the compilation is over, you will get the graphical representation of the results. So this you can see that in a plan and in elevations, the elevation in the section looks like this. So you have different modulus what you have assumed, different depth what you have assumed, and the modulus value computed is also the input parameters are given here. The results can be viewed as a text file, and you can see that the modulus value of a second layer was computed to be 2.017 E4 psi, and the third layer it is 1.831 E power 4. So you can you know that second layer and third layer, both layers are the base layer. So depending on the stress point you consider, the modulus values here are different. Fourth layer is a subgrade layer, and the modulus of a subgrade layer after iterations was found out to be this. So this modulus was computed at the locations, you know, this is at 9 inch and this is at 11 inch and the third one is at 13 inch. And the normal stresses computed at these locations are given here. So at the second layer exactly, which is at the 9 inch, and this is the modulus value computed. You can see 3 normal stresses. So when you can see that these normal stresses value have a negative value. So we said that negative value will be adjusted to 0 in computation of a modulus value. So the negative values were adjusted to 0 for the computation of a modulus value. So this is how the iteration goes on. And finally, once the result converges for the tolerance value we mentioned, you will get the results of modulus at different locations. So for this computed modulus, we have given 2 critical locations. One is at the interface of asphalt layer and a base layer, and second one is at the interface of base layer and subgrade layer. So you will get the critical stresses. So you can see that at the interface, tensile stress is going to control the fatigue damage, which is this epsilon T value minus 1.024 E minus 4. This is your critical stress, which is going to control the fatigue damage at the asphalt layer. Now, rutting on the subgrade layer is controlled by epsilon C, which is vertical compressive strain at the top of a subgrade layer. So, these are the critical strains for this computed modulus. So, it is clear that these values depends on the modulus value. So, if this process is iterated to compute the modulus value, so we have to keep in mind that the modulus is determined at different locations. So, you get the stress at those points first, and then modulus is computed from the determined stress. So, till this process is iterated till the solution converges. So, the now second part of the problem is by using a method 2, that is considering the base course as a single layer and considering the stress point to be at the upper quarter of the base layer. So, you have total 4-inch thickness. Now, with the base layer of from the base layer, you take 1-inch thickness and determine the modulus value at this point, and further determine sigma epsilon r and epsilon z at 2 different locations. So, for these conditions, these are going to be your input. So, for a general informations, we take the type of material to be nonlinear. Damage analysis as of now we are not doing. So, 0, number of period, number of load group each is 1. Okay. Tolerance of numerical integration, if we keep it as the same as a default value. Now, number of layer here is 3. In a previous case, we took it as 4 because we divided a base course into 2 sublayers. Here, base course is considered as a single layer. So, we take a number of layer to be 3 alone, and number of Z coordinate for the analysis is 2, 1 at the first interface and the second at the second interface. So, maximum number of integration default value, these numbers we will keep as such as a default value here. So, this is a general informations. Followed by a general information, we give Z coordinate. That is a point where we need a critical stress and strain. One is at the 8-inch from the top, another is second interface is 12-inch from the top. So, it is 12.001 inch. So, layer input same as the previous case, you have thickness of different layer. The thing is here you have a second layer, base course is not splitted into 2. It is considered as a one single layer. So, you have 4-inch thickness. So, otherwise the Poisson's ratio and the gamma value are same as the previous condition. So, when you go to a moduli value, so we define only one period and you can assume a modulus value again, except first layer, the second and the third layer are a seed modulus which is assumed. You can assume to any nearest number. So, once the modulus input is done, the load input same as the previous type. We give 0 load category as it is a single axle single wheel. Contact radius is 4.5 inch, contact pressure is 75 psi, and YW is 0 because there is no there is only one axial and one wheel. XW is also 0. NR is given as 1 and it exactly at the center of loading. So, RC value is 0. So, once the load input is given, next input is a nonlinear input. In the nonlinear general input, so here the number of nonlinear layer is only 2. In a previous case, we kept the number of nonlinear layer to be 3 because we divided a base layer into 2. So, here number of nonlinear layer is only 2. Maximum number of iteration we will keep it as a default value, and the other parameters are same as that was explained previously. So, in a non-seasonal input, so you have a layer number 2 and layer number 3. Layer number 2, the depth at which we determine the modulus value is at the upper quarter. So, it is 8 inch and upper quarter is 2 inch. So, it is 8 plus 2. So, it is 10 inch here, and at the subgrade layer 1 inch below the interface, it is 13 inch thick, 13 inch. So, this Z value here is 13 inch. So granular layer N clay you give it as 0, and soil subgrade layer you give it as 1, and the corresponding input for a granular layer, that is constant K2 and pressure constant, earth pressure constant, all are given as defined in the previous cases. So you keep in mind you have only 2 layers here. So for the seasonal input, that is for defining a K1 value, and for the minimum K1 value, it is same as defined, but the thing is you will have only 2 layers here, and previous case we had a 3 layer. So now once you complete this input and compile the program, this is the result you will get it. So these are a number of iterations that happened. So total of 6 number of iterations to compute the modulus value. So these are the modulus value, modulus of the base layer and subbase layer at a computed depth, and you can see that these are the values of normal stress you get, and these normal stress value, if you have a negative number, so these normal stresses are adjusted to 0 and the modulus values are computed at the specific locations. So for these modulus value, we determine stresses and strain, critical stresses and strain. So epsilon T, which is critical, is this value minus 1.025 into E minus 4, which is same as your previous case. And here vertical stress that at the top of a subgrade is 2.861 into E minus 4. It is also nearing to the previous case that we determined. So in a nonlinear analysis, to account for the stress dependent modulus value, we use the iteration process. We first give a seed value of a modulus, use the iteration process until the result converges, and finally we get the modulus at different depth, and that modulus is further used in determining stresses and strain at critical locations for consideration or analyzing the nonlinear influence. This figure shows the influence of stress dependent material on the critical stresses, that is tensile strain at the bottom of a HMA layer and the compressive strain at the top of a subgrade layer. So this computation is made for the pavement thickness as shown here. So H1 is considered as a 2 different value. One is 2-inch thickness and other is 8-inch thickness. H2 is considered as a 12-inch thickness. So the value of H2 is considered to be stress dependent, and the equation is given here, 8000 theta to the power 0.5. E3 value is also considered as an elastic material. So E1 is elastic, E3 is elastic, and E2 is considered to be a stress dependent material. In such case, when you vary the pressure intensity, you can see that the tensile strain and the vertical compressive strain increases with the load value. And you can also see that for when the thickness of the HMA layer is thin, that is for a 2-inch thickness, you can see that the influence of nonlinearity at this case and this case is more pronounced compared to the thick asphalt layer. So this is the same case even here. When the layer thickness is small, the nonlinearity influence is more pronounced when compared to the thick asphalt layer here. So we can see that the stress dependent modulus value is more influential in case if you provide a thin asphalt pavement compared to the thick asphalt pavement, and this value is increasing when the load value increases. So that is what we see here. The difference is more when for a higher load category compared to the lower value. So we have seen how the stress dependent modulus value influences the critical stresses and strain. In the next lecture, we will see a damage analysis and how to do a damage analysis using a Kenlayer software. Thank you so much.